This is lecture 17 of A2 metric spaces. Now we're still talking about what it means for metric spaces to be somehow joined up. The last couple of lectures we talked about the notion of connectedness, which roughly speaking means that the space can't be separated into two parts. Now another natural intuitive way that a space might be joined up is if you can always somehow get from one point to another point in the space. And we're going to make that notion rigorous in this lecture. That's what's called path connectedness. So let's take a look at what the definition of path connectedness is. Let X be a metric space, and then we say that X is path connected if the following is true. For any 2 points A and B in X, there is a continuous map from the closed interval 0, 1 into X, such, I'll call that map gamma, such that gamma of naught is A and gamma of 1 is B. So this gamma should be thought of as a path which starts at A and goes to B. So we call, in fact, any continuous map gamma from closed 0, 1 to X is called a path in X. The path connected space is one for which there is a path between any 2 points in that space. Now, let's just make a few comments about paths in general. If you have two paths, gamma 1 and gamma 2 in X, and if the endpoint of gamma 1 is the start point of gamma 2, so if gamma 1 of 1 is equal to gamma 2 of 0, then you can concatenate those paths. So what this means is that you first follow gamma 1 and then you follow gamma 2, and that is also a path. So to be a bit more formal about it, you can define the concatenation gamma 1 star gamma 2. That is the continuous map from 0, 1 to X defined in the following manner. So gamma 1 star gamma 2 of T, if T is less than or equal to a half, then we follow gamma 1. So this is then gamma 1 of 2T. And then if T is greater than or equal to a half, we follow gamma 2. So it's then gamma 2 of 2T minus 1. So it's quite easy to check that this is indeed a continuous map, and it consists of putting gamma 1 and gamma 2 together. Another operation you can do on paths is to look at the opposite of a path gamma, and this consists of traversing the path gamma in the opposite direction. So if gamma from closed 0, 1 to X is a path, then we can define its opposite, gamma minus, to be the map defined by gamma minus of T is gamma of 1 minus T. And if gamma starts at A and finishes at B, then the opposite path starts at B and finishes at A. So those are a few basic operations that you can make on paths. And the reason I've described those operations is because they are important in proving the following result. So let X be a metric space, and then we can define a relation tilde on the space X in the following way. So we say that A tildes B if and only if there is a path, gamma, from closed 0, 1 to X, which starts at A and finishes at B. That is to say, gamma 0 equals A and gamma 1 equals B. So just to recall, a space is path connected if every pair of points in X are equivalent under this relation. So when X is path connected, this relation is just the trivial relation in which every 2 points are related. But in general, this relation might be non-trivial, and the lemma is that this is nonetheless an equivalence relation. So let's prove that. We first need to show that A is equivalent to A. So we need to find a path which starts at A and finishes at A, and that's very easy. You just take the path which takes the constant value of A. So gamma of T is always A. We need to show that if A tildes B, then B tildes A. So if there's a path from A to B, then there's a path from B to A. And that can be done using the opposite path. So if gamma is a path from A to B, then gamma minus is a path from B to A. And then finally, we need to show transitivity, and that's where we can use the join of two paths. So if A tildes B and B tildes C, well then there's a path gamma 1 from A to B and a path gamma 2 from B to C. But then the join gamma 1 star gamma 2 would be a path from A to C. So we've shown reflexivity, symmetry, and transitivity of this relation tilde, therefore it's an equivalence relation. And therefore it partitions the space X, the metric space X, into equivalence classes, and those are called the path components of X. So if you're in one path component, any pair of points is joined by a path. If you've got 2 points in different path components, they're not joined by a path. And a space X is path connected if and only if it's got a unique path component. So we've got this notion of path connectedness, and it's natural to ask, what is the relationship between the notion of connectedness that we talked about earlier in this chapter and this new notion of path connectedness? And that's what I want to explore in the remainder of this lecture. So the first main theorem is that path connectedness is a stronger notion than connectedness. So a path connected space is always connected. So let's look at the proof of that. So suppose I have a path connected space X, and then I'm going to use the criterion for connectedness in terms of continuous 0, 1 valued functions. So suppose F is a continuous map from X to the set 0, 1. What I want to show is that F is constant. So as I showed a couple of lectures ago, that is equivalent to X being connected. So F here is continuous and takes values in the 2-point space 0 and 1. Well, let's take an arbitrary pair of points A and B in X. Then X is a path connected space, and so there's a path, gamma. That's a map from closed 0, 1 to X, with gamma of 0 equals A and gamma of 1 equals B. So gamma starts at A and goes to B. Now consider what happens if you compose that path with F. So you look at F of gamma of T. So that is a composition of two continuous maps, and therefore it's continuous. And it maps from closed 0, 1 to the 2-point space consisting of the points 0 and 1. But we showed in the last lecture that the closed interval 0, 1 is connected. And therefore, if you've got a continuous map from that connected space to the 2-point space 0, 1, well, then it's constant, because that's an equivalent formulation of what it means to be connected. So this composition F composed with gamma is constant, and therefore F of A equals F of B. So F of A is equal to F of gamma of 0, which is equal to F of gamma of 1, because F composed with gamma is constant, which is equal to F of B. But A and B were just arbitrary points of X, and I've shown that F of A equals F of B, but just arbitrary points A and B. And therefore, F is indeed a constant map, and therefore X is connected. Okay, so path connected implies connected. Now what about the other direction? Does connected imply path connected? Well, it turns out that the answer to that is no in general, and we'll see an example at the end of the lecture. But the answer is yes sometimes. So the answer turns out to be yes if X is actually a normed space. So we'll prove that positive result first. If you have a connected open subset of a normed space, then it's path connected. So that's a theorem. Let's write X for this connected open set. And then I claim that any path component of X is open. So let's prove that claim. Let P be a path component of X. So let's just remember what this means. It's one of the equivalence classes under the equivalence relation that A tildes B if there's a path from A to B. So suppose that P is one of those equivalence classes, and let's take a point A in P. Now X is open, and so there is a little ball of radius epsilon, contained in X, about A. Let's let B be a point in that ball. And then I can write down the following path gamma from A to B. So this is a path in X, well, in the underlying normed space. Gamma of T is 1 minus t times A plus t times B. So that's a continuous map. Gamma of 0 is A and gamma of 1 is B. Now I claim that its image is contained in this ball of radius epsilon about A. And the reason for that is that if I write down the norm of gamma of t minus A, in other words, the distance from gamma of t to A, well, using simple properties of the norm, that's t times the distance from A to B. And because t lies between 0 and 1, that's at most the distance from A to B, which is less than epsilon. And that's true for any t between 0 and 1. So all of these gamma t's lie in this ball of radius epsilon about A, and therefore they all lie in X. So I've exhibited a path in X that joins A to B. And therefore B is in the same path component of X as A. So I've shown that the whole of this ball of radius epsilon about A is in the same path component of X as A. And therefore this path component is open. Now we've already shown that path components partition X. And so if there was more than one of these path components, well then we could write X as a disjoint union of non-empty open sets. And that's contrary to the assumption that X is connected. And the only way out then is to conclude that there's only one path component, and therefore that X is path connected. So in normed spaces, at least for open subsets of normed spaces, connected implies path connected. So finally, we come to an example. I think one should be aware of this example, but I think the proofs in connection with this example are non-examinable. So this example is a famous example called the topologist sine curve. And this is an example of a connected subset of the plane R2, which is not path connected. So theorem, there's a connected subset of R2, which is not path connected. And here's a picture of what it looks like. I'll give the formula on the next slide. So it's a sort of sine curve that becomes increasingly wiggly, if you like, as you tend towards 0. So just have that picture in mind, but I'm now going to define mathematically what this topologist sine curve is. So it's the following subset A of R squared. It consists of the points x comma sine 1 over x for x strictly greater than 0 and less than or equal to 1, together with the vertical line segment of points 0 comma y with y greater than or equal to minus 1 and less than or equal to 1. So that's what the set A, called the topologist sine curve, is. So I claim that that is a connected subset of R2, which is not path connected. So why is it connected, first of all? Well, one could convince oneself that this set A is the closure just of the sine portion of it. So if E consists of the points x comma sine 1 over x, and if I take the closure of E, then I get that vertical line segment consisting of the point 0, y for y enclosed minus 1 up to 1 as well. So A is the closure of E. Now E is connected because it's the image of a connected set, namely half open 0, 1, under a continuous map. So that's the map that sends x to x comma sine 1 over x. So E is a connected set, but we showed a couple of lectures ago that the closure of a connected set is connected, and therefore A is connected. So the topologist sine curve is connected. Now, why is it not path connected? Well, the intuitive reason is that somehow you kind of can see that how would you get from the origin 0, 0 to, let's say, the point 1 sine of 1? It's somehow going to be impossible to pass through that extremely wiggly region of the curve in a continuous way. Now, that's not a proof, but that gives the idea of why it's not path connected. There is no path from the origin to the points, and to any point, in fact, in E. So why is A not path connected? Well, let's try and prove this. Suppose we did have a path gamma from close 0, 1 to A, the topologist sine curve, starting at the origin 0 and finishing at the point 1, 0. So let's write L for the vertical line consisting of the points above the origin. So 0 x coordinate and y coordinate between -1 and 1. And so A is E, the sine part of the curve, together with this vertical line L. Now L is closed, it's just a line segment, and gamma is continuous, and so the inverse image of L under gamma is closed. And in particular, it contains its supremum T. So what this means is that gamma kind of hangs around in that vertical line segment L for a while. It starts there at time 0, T equals 0, and it hangs around there for a while, and there'll be some supremum T of points for which it's there. So gamma of T lies in this vertical line segment L, but if U is strictly bigger than T, then gamma of U lies in E, the sine portion of the curve. So it sort of somehow is supposed to jump from the vertical line segment L into E at this point T. So could that possibly happen? Well, let's first of all look at the projection onto the y-axis. So this is the projection that maps the point xy to y. So this projection py is continuous, and so is the composition of py with gamma. So that's a map from close 0, 1 to R. And, well, in particular, it's continuous at the point T, and just applying the definition of continuity, what this means is that there is the definition of continuity with epsilon equals 1, there will be a delta greater than 0, such that py of gamma of u1 and py of gamma of u2 are at distance less than or equal to 1 whenever u1 and u2 are between t and t plus delta. Now here I'm using the fact that the projection onto the y-coordinate composed with gamma is a continuous map at this point t. So we'll come back to that equation. We'll call that 1. So the variation of the y-coordinate is bounded by 1. Now let's look at the projection onto the x-coordinate. I mean x-coordinate here, not x-axis. So let px be the projection onto the x-coordinate. That's the map that sends xy to x. So the composition of px with gamma is also continuous because gamma is continuous and px is continuous. And so by the intermediate value theorem and the fact that, so the projection of the x-coordinate of gamma of t plus delta is not 0, and therefore it's positive. So this is by the assumption that t is the supremum of points for which the x-coordinate of gamma of t is 0. So the x-coordinate of gamma of t plus delta is strictly positive, and the x-coordinate of gamma of t is 0. And therefore, by the intermediate value theorem, the composition of px and gamma applied to this interval from t up to t plus delta, well, it contains a whole interval. So if c here, if little c, which is positive, is the value of p of x, the x-coordinate of gamma of t plus delta, then on the interval t up to t plus delta, the x-coordinate of gamma takes every value between 0 and c. So that's the intermediate value theorem. But as x ranges over values between 0 and c, so strictly bigger than 0 and less than or equal to c, well, sine of 1 over x takes every value between -1 and 1, in fact, infinitely often. So that's because the sine of 1 over x is kind of has infinitely many wiggles in any interval 0 up to c. Well, and therefore that means that there must be some values u1 and u2 in this closed T up to T plus delta, whose y values, such that the y values of gamma of u1 and gamma of u2 are respectively 1 and minus 1. But if they're 1 and minus 1, then the distance between them is 2. And that contradicts what I showed earlier. So just go back to the previous slide. I've shown that in this little interval from T up to T plus delta, the distance between the y coordinates of the gammas is never more than 1. But then, by looking at the x coordinates, I've shown that in fact, in any such interval, T up to T plus delta, there must be some y coordinates of gammas that are both 1 and minus 1. And these two statements are contradictory. Okay, so the proof that the topologist sine curve is not path connected is tricky, definitely non-examinable, but I think it's a thing to be aware of. So it's a classic example showing that you can be connected, but not path connected. Okay, that's the end of chapter 7 of the course, in which we talked about various different notions of what it means for a metric space to be joined up. This is lecture 18 of A2 metric spaces, and this is the first lecture corresponding to chapter 8 of the course. Now, I just want to make a few preliminary remarks on chapters 8 and 9 of the course. So in this chapter, chapter 8, we're going to talk about the notion of sequential compactness of a metric space. And in chapter 9, we'll talk about the notion of compactness. Now, one thing we'll show in chapter 9 is that, in fact, these two notions are one and the same thing. So a metric space is sequentially compact if and only if it's compact. And sometimes, because of that fact, when people introduce the notion of sequentially compact, they actually just use the word compact. And in fact, that's been done in the schedules for this course previously. Now, I really don't like doing that for a few different reasons. But the most important one is that in topological spaces, so in more general context than metric spaces, the two notions are actually different. I also think it's quite confusing to introduce one word for two different concepts before you've shown that they're in fact the same concept. So I will be very carefully referring to sequential compactness in this lecture and compactness in the next lecture, and only at the end of the next chapter. Only at the end of the next chapter will we really show that they're the same concept. Okay, so we'll turn now to introducing the notion of sequential compactness. Now, before I can even get to that, I need to just make sure that we're clear about what is meant by subsequences. So let X be any set, and suppose I have a sequence Xn, n equals 1 to infinity, so x1, x2, x3, and so on, of elements of X. So we call that sigma. Now, what is meant by a subsequence sigma primed? It's quite hard to notate these, so we have to use a double subscript notation, x sub n sub k equals 1, 2, 3, and so on. So here, n1, n2, and n3, etc. are an increasing sequence of natural numbers. So anything like that is called a subsequence of sigma. And just to give you an example, if I've got a sequence x1, x2, x3, x4, etc., then if I just look at the sequence formed by looking at square indices, so x1, x4, x9, x16, and so on, that is an example of a subsequence of the first sequence. Okay, so that's just to clarify what's meant by subsequences. And it's important to do that because the notion of sequential compactness uses crucially this idea of a subsequence. So let's turn now to what that definition is. Let X be a metric space, then X is said to be sequentially compact if any sequence of elements in X has a convergent subsequence. So no matter what sequence Xn from n equals 1 to infinity you take, you can pass to a subsequence of it that has a limit. Let's give some examples. So the closed interval 0, 1 is sequentially compact, and that is what's usually known as the Bolzano-Weierstrass theorem. So you saw that in the prelims course in real analysis. The open interval 0, 1 is not sequentially compact. For example, if I take the sequence xn in which the element xn is 1 over n, that does not have any convergent subsequence. The easiest way to think about that is to think of open 0, 1 as being contained in the whole of the reals, and then the sequence xn has a limit, namely the point 0. And if you have a sequence tending to a limit, then any subsequence of that sequence tends to the same limit. So any subsequence of this sequence xn tends to 0 when considered in the whole of R. And because limits are unique, it cannot also tend to a point of open 0, 1. So this sequence has no subsequence that converges to a point of open 0, 1. Therefore, open 0, 1 is not sequentially compact. What about something else? The set of rational numbers in closed 0, 1 is not sequentially compact. And for example, I've written down here a sequence of decimal approximations to pi minus 3. So just truncate the decimal expansion of pi at increasing numbers of decimals. So that goes 0.1, 0.14, 0.141, 0.1415, etc. And that has no convergent subsequence. Again, probably the easiest way to see that is to think of this space of rational numbers in closed 0, 1 as sitting inside the real numbers. Then the sequence converges to pi minus 3, which of course is not a rational number. So any subsequence of it converges to pi minus 3, and in particular, no subsequence of it converges in the rational numbers. Finally, well, the real line itself is not sequentially compact, and that's basically because it's not bounded. So if you take the sequence in which xn equals n, then that really definitely has no convergent subsequence in this space. So no convergent subsequence in R. Well, let's turn a little more generally to an elaboration of that last point. So we saw that the real line's not bounded, and so it's not sequentially compact. And actually, it turns out that in general, for a metric space to be sequentially compact, it must be both closed and bounded. So we'll prove that now as a lemma. The lemma, a sequentially compact subspace of a metric space is closed and it's bounded. So let X be the big metric space and let Y be the subspace of it that's supposed to be sequentially compact. So I want to show that Y is closed in X and that Y is bounded. Well, suppose first that Y is not closed. Then I know that one way of describing when subspaces are closed is that the limit of any convergent sequence of elements of that space is in the space. So if Y is not closed, what that means is that there must be a sequence, little y sub n, n equals 1, 2, 3, and so on, of elements of big Y, which tends to a limit, let's call it A, but A is not in big Y. So there's a convergent sequence whose limit is not in big Y. Well, any subsequence of that sequence also converges to A. And therefore, because limits are unique, it cannot converge to an element of big Y. So actually, this is the same argument that we've already seen twice on the previous slide. First, to convince ourselves that open 0, 1 is not sequentially compact, and then to convince ourselves that the rationals are not sequentially compact in closed 0, 1. So a sequentially compact subspace of a metric space X must be closed in that space X. Now suppose that Y is not bounded. Well, pick any point Y0 in Y. I mean, if Y is not bounded, it's certainly not empty, so it has a point Y0 in it. And now pick a sequence Yn of points increasingly far away from that Y0. So for each n, pick a point Yn such that the distance from Y0 to Yn is at least n. And I can always do that, otherwise capital Y would be bounded. So if there was an n for which I was unable to do that, well then the whole of capital Y would lie in the ball of radius n centered on Y0. So I've got that sequence of Yns, and suppose that it had a subsequence, which I'll notate with this rather horrible double subsequence notation. So suppose I had a subsequence Y sub n sub k, k equals 1, 2, 3, and so on, that converged to a point B. Well, by the definition of converging to a point B, that certainly means that if k is big enough, then the distance from y sub n sub k to b is less than 1. So that's applying the definition of limit with epsilon equals 1. But then I have the following inequalities. The distance from y0 to b, well, by the triangle inequality, it's at least the distance from y0 to y sub n sub k minus the distance from y sub n sub k to b. But the distance from y0 to y sub n sub k is at least n sub k by definition. And the distance from y sub n sub k to b is less than 1 by the choice of k, as I've just remarked. So I've shown that the distance from y0 to b is at least n sub k minus 1. But as k tends to infinity, this tends to infinity. And that's nonsense, because the distance from y0 to b is some definite real number. It's not greater than or equal to arbitrarily large positive natural numbers. So that's a contradiction. And therefore, if y is not bounded, I manage to find a subsequence without a convergent, a sequence without a convergent subsequence. Therefore, y could not be sequentially compact. So that's a sort of basic property of sequentially compact metric spaces. We'll show more properties of them in subsequent lectures. The last thing I want to do in this lecture is, well, I want to prove actually two more things. So I now want to show something in the opposite direction, which is that a closed subset of a sequentially compact metric space is sequentially compact. So in the previous lecture, I showed that sequentially compact implies closed and bounded. Now I'm going to show that if your big space X is sequentially compact and you have a closed subset Y, then Y is sequentially compact. So let's prove that. Let X be the big space and Y the closed subspace. So we're assuming that X is sequentially compact, and I want to show that Y is sequentially compact. Let's take a sequence little y sub n of elements of big Y. Well, you can also think of it as a sequence of elements of big X. And X is supposed to be sequentially compact, and therefore this sequence has a convergent subsequence. So let's say it has a subsequence converging to A. But Y is closed, and the limit of any convergent sequence of elements of Y therefore lies in Y. And so this A, in fact, lies in Y. So what I've shown is that for an arbitrary sequence of elements of Y, it has a subsequence which converges in Y. Therefore, Y is sequentially compact. So now I come to the last thing that I want to do in this lecture. This is something that, I mean, I think it's mildly interesting, certainly in its own right. But the reason I'm covering this now is that this will be specifically needed in the complex analysis part of the course later on. So this is a lemma about thickening. And the lemma states the following. Suppose you have a metric space X and you have a sequentially compact subset K of X, and you also have an open set U that contains K. So K is contained in U and U is contained in X. K is sequentially compact and U is open. Then the conclusion is that you can thicken up K a bit. And this means the following. So it means that there's some positive epsilon such that if I put a ball of radius epsilon about every point of K, so it's the same epsilon for every point, then the union of all of those balls is still contained in U. So I think of that as an epsilon thickening of K. So let's prove that. Well, suppose that's not true. Then it's certainly not true with epsilon being 1 over n, for n an arbitrary natural number. Well, let's think about what that means. So that means that if I try and thicken K by 1 over n, it's not contained in U. And what that forces us to conclude is that there is a point xn in K such that the ball of radius 1 over n about xn is not contained in U. And if that ball is not contained in U, well, that means that there must be a point in that ball that's in U complement. So we'll choose a point yn in U complement whose distance from xn to yn is less than 1 over n. Parenthetical remark here, I've again used this thing called the axiom of countable choice here. So end of parenthetical remark. Now K is a sequentially compact space, and I've got a sequence xn of elements of K, and so it has a convergent subsequence. So let's call that subsequence x sub n sub little k. Little k is 1, 2, 3, and so on. And that subsequence converges to a point P in big K. But the corresponding points y sub n sub little k, well, their distances from the x sub n sub little k's tend to 0, and therefore that sequence y sub n sub k also converges to P. But the y sub n sub k's, they lie in U complement, and U is open, so U complement is closed, and therefore their limit, that is to say P, also lies in U complement. So if you have a convergent sequence of points in a closed set, then their limit is also in that set. But now I find this point P that lies in both K, capital K, and in the complement of U. But that's impossible because I'm assuming that K is contained in U. So K intersect the complement of U is an empty set. So that thickening's lemma will be used again at some point during the complex analysis part of this course. And in the next lecture of this course, we'll get back to looking at some more properties of sequentially compact metric spaces.